We're going to be talking here about rotational motion. And to start off with, what are these parameters that we're talking about? Well, first of all, translational motion is anything that moves along a straight axis. So this is what we've been talking to up to this point. But now we're going to be talking about rotational motion, which is when an object turns about an axis. So rotational motion is on an axis. Translational motion is along a straight axis. So you can have either one independent of each other, or you can have both of them happening at the same time, as with a car, which we'll deal with in the next chapter, which is rolling motion. So anytime we have rotation, we're typically dealing with 3 dimensions. So the way that this book defines it is they talk about the z-axis usually is the one that's being rotated. So if you have an object here, let's say this is an object here, this is supposed to be a 3-dimensional object, and you have a rotation axis, which is what this is. So the rotation axis is this one here in green. So that's what you have here, the rotational axis going through that origin. And then you have something called a reference line. And the reference line is what you're going to use to measure your angular measurements in. So the reference line is a part of the body perpendicular to the axis of rotation. Okay, now this is what we call a rigid body. So this 3-dimensional shape is a rigid body, and this is a body that can rotate with all of its parts locked together without any change in shape. So we talked about in class that an example of like a hurricane is not an example of a rigid body because all of the parts are not interlocked. When you have a rigid body, the further away you are, the faster the translational motion is. So as you get further out, the tangential speed becomes faster at this point. Okay, the tangential translational speed. So a hurricane is the opposite. The hurricane, the wind speeds actually get faster towards the center, so that is not a rigid body. Next, we're going to talk about angular position. So angular position here is defined in radians. So the term that we use here is theta here, and that is going to be the angular position. So the angular position starts here typically, doesn't have to start here, but in this case, at the unit circle, and it moves. In this case, we're moving this way, okay? And this is your reference line, this line right here that we talked about before. So I'll do it in a different color here. So your reference line is rotating about an axis, and your rotational axis is here. So this is the rotational axis, and the dot means it's coming out of the page. If we had an X, it means it's going into the page. So dot is out, and X is into the page. So it's rotating here, and you have some radius here, and then you have your arc length there. Arc length, by the way, is going to be the letter S. So let's choose a different color for that. Let's choose this color here. This is arc length S. That's the path that something takes. So that's what this is here, S. And then when you have the radius here, the radius is just the extension out here to this point. And we'll make that one, let's make that one purple. And that's going to be your R out there, and that's what this is here. So you have your theta here. You are moving an object around a rotational axis here. Here's your reference line. And the path that it traces out is this S, or this arc length. So the definition of arc length is just going to be r theta. So if we take these and we put them together over here, that S is going to just equal r theta. So that's just taking this equation and rearranging it. So you may have seen that before in math as, you know, the circumference times the ratio of the angles, you know, like 2 pi r times theta over 360 gives you the arc length. But this is the most efficient formula to talk about arc length. Theta is in radians, r is in meters. And then that's going to give you S, which is the path out here along this rotational axis. And of course, this is your reference line here. So very important term here, because now we're talking about curves. We're not talking about straight lines. And the reason I use the letter S, I talked about this in class. S, you know, sometimes they use this S for arc length, but that kind of looks like the number 5, so it's kind of confusing. So I just use a lowercase s to denote that. These are some points here that you may have seen before in math, but I'll just point them out here. 1 revolution is 360 degrees, or 2 pi radians. So if we go all the way around, it's 360 degrees, or that's 2 pi. Each time we're going to a different terminal, we're moving pi over 2, so we're going 0, pi over 2, pi, 3 pi over 2, 2 pi. 1 radian is 57.3 degrees, or 0.159 revolutions. Okay, next we're going to talk about angular velocity. So angular velocity is the speed of rotation about an axis. So if we talked about before about our thetas here. So if our reference line is here, this is our reference line here, and then the reference line moves to another point in time here at t2, that those two angular positions change across time. So you have here theta 1 and theta 2. So theta 1, theta 2. So theta 2, theta 1. And then the change of those creates a delta theta. So from here to here, you have some change of theta. Then you can get an average omega here. So omega, we'll do that in blue actually. So omega is going to be blue here. So that stands for angular velocity. The line above this means that we're talking about the average. So the average, we're just talking about final minus initial over final minus initial. So delta theta over delta t, and that's going to be in radians per second. Now, we can find an instantaneous angular speed, omega, which of course is the limit as t approaches 0 of the average velocity, delta theta over delta t, or that just becomes d theta dt. Now notice this is very similar to the linear equations when we talk about that v is dx dt. That's basically what that's saying, but in terms of theta. So that's important to note that there's a similarity here. All right, so next is going to be angular acceleration. So angular acceleration is the symbol alpha, and this is going to be measured in radians per second squared. So that means that you're spinning faster and faster and faster, or slower and slower and slower. Okay, you'd be slowing down or speeding up. And that line above it means average, just like the omega. So it's final minus initial omega over final minus initial t, or delta omega over delta t. Alpha instantaneous is the limit as delta t approaches 0 of delta omega over delta t, or d omega over dt. And again, this is very similar to just saying dv over dt is the acceleration. So a question is, are angular quantities vectors? In essence, yes. They use the right-hand rule number 2 to define the direction. So you curl your fingers in the direction of the omega, okay, of the speed, the direction of the speed, and then your thumb will give you the direction of the vector. And so this is a picture of a hand here, a right hand. You're curling your hand around the axis of rotation, and the thumb points in the direction of the omega, which is straight down. Now there is one exception for this. The exception is if you're talking about angular displacements, they cannot be treated as vectors. So the order of the rotation makes a difference. So with regular displacement, remember, it doesn't matter how you get to start to finish, right? Like if you go, if we're talking about x displacement from here to here, if I go from here to here to here, it's the same as if I went from here to here to here, right? But angular displacements, that's not the case. If I rotate along different planes, like xy plane, yz, and then or if I do yz, xy in that order, in those specific orders, I get a different outcome. So for that reason, we don't say that the actual displacement is like a vector in that case. Now, rotations with constant angular acceleration, they mimic the kinematics equations. So remember down here, we have the kinematics equations on this side. Remember these when you have a constant acceleration. If you have a constant angular acceleration, you have very similar equations. So instead of V here, we have omega. So omega equals omega initial plus alpha t. So over here it's V equals V initial plus AT. Here we have delta theta equals omega initial plus 1/2 alpha t squared. Over here we have delta x equals V0 t plus 1/2 AT squared. Over here we have omega squared equals omega initial squared plus 2 alpha theta. And here it's just V squared equals V initial squared plus 2a delta x. Same thing here, delta theta equals omega initial plus omega over 2 times time, and this equals delta x equals v initial plus v over 2 times time. So the same exact equations, but again, only valid with a constant acceleration. Only valid with a constant acceleration. Now we're going to talk about relating linear and angular variables. So why is this important? Well, depending on where you are on the axis of rotation, you're going to have different linear components. So the actual position at any given point is going to be r theta. S. S would be like on a circle. So if we're talking like this, we have a circle. S would be, we start here, it's the actual position at any point, like right here, this position right here. It could also be delta S. If it's delta S, you're talking about arc length. So again, you have theta here, you have r, and your S is this distance here that travels from here to here. So S equals r theta. Theta has to be in radian measures for this to work. Otherwise, you got to get into, 2 pi r times theta over 360, and it's a much longer equation. This is much more direct and efficient. Arc length, r theta, period. That's it. All right, so your speed will change as a function of your radius. So what does that mean? Well, depends where you are. So v tangential is here, and that's the speed that's tangent to this path of motion here. And it's going to change depending upon where you are. Remember that omega is the same at all places on this circle. It's the angular speed. It doesn't matter where you are. The change of theta is going to be the same here, from here to here, from here to here. But tangential speed is ds dt, which is r d theta dt, because r is the radius, and which equals r omega. So tangential speed is going to be r omega. R omega. So that's always true. Now, it's a linear function and it's direct variation. So what does direct variation mean? We talked about this before. Direct variation is simply what chemistry is based off of. That's why you can do dimensional analysis and figure things out just by messing with the units, because it's a function, it's a linear function, but there's no intercept. Okay, so at zero there's no speed. So as you get further away from the center, the tangential speed increases, and then it reverses on the other side. So it goes this way on the other side. So you're starting to see some patterns here. Arc length, r theta, tangential speed, r omega, and the period t, 2 pi r over v, or 2 pi over omega. Now there's an equation down here that I like to refer to as one of the master equations. I think the work equation is another one that we talked about. Work net is conservative plus non-conservative. But this is like a master equation because it relates many quantities here. Omega is 2 pi over t. So if I want to find the period, I set this equal to this. Omega is 2 pi f, 2 pi times the frequency. If I want to find the frequency, I set this equal to this. These represent simple harmonic oscillators. Square root of g over L is a pendulum, a simple pendulum that doesn't have a rod on it, an inertial mass, which we're going to see. And then the square root of k over m is a mass spring oscillator. So if I want to find the period of a pendulum, I set this equal to this. Solve for t. If I want to find the period of a mass spring oscillator, I set this equal to this. Solve for t. If I want to find the angular frequency of a pendulum, I set this equal to this, square root of g over L. If I want to find the frequency of a mass spring oscillator, I set this equal to this. It's really amazing, this equation. It goes a long way. It really does. It's good. So this is just more talking about the velocity being tangential to the path. So there's your axis of rotation. Again, the dot being out of the page, radius, tangential velocity there. So acceleration. Now this one is going to be two components. You're going to have a tangential and you're going to have a radial. So your tangential is this component here on the outside, and that is a function of how far away you are. It's another direct variation equation. So tangential, we know tangential is just dv dt, right? But we know that tangential speed is r omega, so it's d omega dt times r, and d omega dt is alpha. So the tangential acceleration is just r alpha. So that's the tangential speed at that point. So again, depending upon where you are, that's going to change. Why is that important? Well, it's important because alpha never changes. Alpha is the same everywhere. Here's alpha. If I'm getting faster and faster and faster, at any given snapshot, alpha is just going to be the same. But the tangential could change, and we talked about that using the fishing boat example. If you're in a boat and you're in one of those tuna towers in the boat, let's say the boat is here, and then there's the bridge here, and then they have these towers up where people go to look for the fish. There's a person up there, right? That when the boat rocks back and forth, that person is going to experience a much greater tangential acceleration than the person down here, right? And so what happens is a lot of times when you get these very strong storms that come up, the person that's up here in the tower, they can't come down because they'll get thrown out of the boat. It's like it'll literally sling you out of the boat. So that matters. It matters where you are. Now there's a radial component here. The radial component, we've talked about this before. This is just v squared over r. This is the centripetal acceleration. And so all you need is a tangential speed for that radial component to appear. You don't need to be going faster and faster or slower and slower. You just need to be moving in a circle. This one, the tangential, you need to be spinning faster and faster or slower and slower. This one, if you just have a speed, you have it, right? And so this one's going to be r omega squared. And the reason is because if you have v squared over r, remember v is r omega, so r omega squared over r, that's going to be r squared over omega squared r, and then the r's cancel, and so you end up with r omega squared. So important to know both of them also, that since these are two components of my system, let's say that I make my axis on that particular moment, let's just say I did make my axis like that if it's rotating, that I have a net acceleration. So what's the direction of the net acceleration? Well, if I have my radial in like this, and I have my tangential out like this, we can use the parallelogram method to find out where my net acceleration is. So the net acceleration is going to follow that parallelogram. So if I make the parallelogram here on this side, and if I come over here and I make the parallelogram here on this side, the net force is going to be straight across like this. So that is my net, the magnitude of my net acceleration at that point. So it's something important to consider when you have a multiple choice question on the AP exam or some exam. They may ask you a question like this. All right, next topic is kinetic energy of rotation. Why is this important? This is important to understand the concept of rotational inertia or the moment of inertia. When we're rotating, remember we have different terms. We have like alpha, we have omega. So we're going to have a different term for mass. And we're going to call that the rotational inertia. Anything that has inertia is something that's going to resist motion. If you have a mass, it's going to resist a motion when you put it on it. So how do we define that? Well, if we have a series of particles here moving on a line, we say the kinetic energy is 1 half m1 v1 squared plus 1 half m2 v2 squared plus 1 half m3 v3 squared. So that makes sense. We've seen that before. Now we're going to see this summation come into here. Summation later on means integration. So right now we're talking about a series of point masses. Okay, so summation of the kinetic energy is 1 half mi squared vi squared. Notice they both have a subscript right now. Okay, but what if we're rotating? Notice that they're all going to have different speeds at different points, right? Everybody see that? They're all going to have different speeds at different points. So I'm going to take this v equals r omega, and I'm going to substitute it into the speeds. Now, something interesting is going to happen here. When I substitute this r omega into here, I'm going to have omega r here, but the subscript is going to disappear from the omega. So that's important. Let's talk about that for a second. Notice here that I still has a subscript and ri has a subscript because you have some, let's say m1 here and you have r1 here, right? Some radius 1 here and mass 1, and you have some speed 1 here, okay? But omega is the same everywhere, right? So what happens is you distribute this across and you're going to get 1 half sum mi ri squared omega squared. And so what I did was I distributed the omega squared out of here to show that this is the only part that's taken the sum in here. This mr squared is what we refer to as the rotational inertia, the sum of them. So when I add up all of these points, these are going to be the points that are going to resist my motion to it, my torque that I can apply to it. It's going to resist it. And that's going to be called rotational inertia. Very similar to like a mass resists you when you try to push it. This term is going to be called the letter I, rotational inertia. Now this is for point masses. So it's going to be very different when we get to solid and rigid bodies because we're going to have to integrate across the geometric shape of that object. And we're going to assume a constant linear mass density or volume mass density depending on the situation. So this rotational inertia tells us how the mass is distributed about the axis of rotation. And it's going to determine how easy or how hard it is to rotate something. So here's a little summary down here. I is going to be the sum of mi ri squared. And the units are going to be kilograms meters squared. If I'm talking about kinetic energy of rotation, it's going to be 1 half I omega squared. So we treat all of these mr squareds and you add them up, we treat them all of those added up, remember all of those points that we're trying to rotate, as one unit, as one measure, I. Okay, and then when we get to a solid object that's a rigid body, we're going to integrate across the geometry of that shape. Now, the units are still joules with kinetic energy, but this is dealing with rotation. Now, rotation is we're going to see in the next chapter that it's going to exist with linear kinetic energy. So this is K rotational, but you also have K linear. So it takes energy to spin something and it takes energy to move something on a straight line. So if you're spinning and you're rotating, it takes energy to do both. All right, so finally, this is just a visual display of how easy or how hard it is to rotate something. So if I have an object here, like a rod, and my rotational axis goes through the rod, and I want to rotate it this way, it's much easier to rotate something this way because the distance, the r, is much smaller, right? That radius of rotation is much smaller. But if I have a rotational axis here, now I have all of these different masses, which I'm going to have to add up, right, through an integral. But imagine if I just had, 3 point masses out like this. that it's going to be harder to rotate because these all have different radiuses going out. And the further that we get, remember it's a function of mr squared, the further out I get, the harder it is it's going to be to rotate that. So that's just like a visual of the differences of rotation and the difference in difficulty to rotate something. But this all comes into play in the next section when we start integrating across, because this is going to have a linear mass density as we go across. So just to kind of remind you what that is, lambda is going to be the total mass over the total length. And if I want to know the mass, let's say that this is an x here, let's say that this is x, and I want to know the mass going across from some point, okay? The mass as a function of x, if I'm moving along the x here, it's going to be lambda x, because depending upon how much x I cover, it's going to give you an idea of how much mass you've covered. So linear mass density, that's going to tell you how much mass you have at any position, how much mass you've covered at any position. Now, we'll see later, depending upon where you start this integration, if I started here, if the length of this rod is L, if I started from the center, then I might go from negative L over 2 to L over 2. If I started from here, if I rotate it from here, I'll go from 0 to L. But again, we'll see that in the next section.